Hello and welcome to Toddcast 51. In this Toddcast, we will look specifically at free radical halogenation reactions, one of the more common reactions you see of this ilk in organic chemistry. We'll look in pretty good detail of the reaction mechanisms, so what we learn in this one, we can apply to other mechanisms, and we'll see. So in our world, oxidation reactions with O2 are the most common. They occur all the time. Polymerization reactions, where we make plastics, a lot of times those are free radical, those are fairly common. Our halogen reactions aren't so common anymore. We finally realized halogens aren't such a good thing. But classically, it's what we teach because it is a simple example that gives us the foundation. And so I'm going to be a big proponent of understanding how these things work and then down the road being, I don't know, willing to replace what we learn about a Cl-Cl bond and apply it to an OO bond in a peroxide. And you'll be doing the exact same thing chemistry wise, just in a more practical sense. But for today, or I should say this podcast, we're going to focus on the halogenation. Okay, so free radical reactions. Um, there's a few different types, as I alluded to. So the first of which, uh, initiation reaction, and you can classify it the following way. Initiating is getting something started. It's where you go from no free radicals to two free radicals, and you can almost always assume it is initiated by light. So if you have a ClCl, if the right amount of energy goes in, this bond can break in that fashion, and you will get, lo and behold, two chlorine radicals. Okay, that's initiation reaction. You start with no radicals, you finish with two. You break a sigma bond or a pi bond. In this case, we're breaking a sigma bond, and you end up with two radicals. Okay, I'm going to clear that. Then there's a propagation reaction, where one radical in the reactant turns into a different radical in the product. So it keeps it going. It sustains it. So you start with one, you finish with one, which means the total number of radicals has neither gone up nor gone down. So you've just simply propagated the process. And then termination. Termination, let's say I have an H free radical and a chlorine free radical left over from before, let's say. These two can form HCl like that. So two free radicals, the H and the Cl, combine to form no free radicals, meaning you terminate the existence of free radicals that way. So three basic reactions: initiation, where you generate two radicals; termination, where you get rid of two radicals; and propagation, where you just break even. One free radical turns into a different free radical. Okay, so let's go ahead and look a little cleaner at it. I did chlorine, but we'll do it generically as X. No lone pairs are shown here, but you should note that there's lone pairs all around here. So the octet is complete when it begins, but you lose the octet. This can also be O, like peroxide, hydrogen peroxide, for instance. In weird instances, it can be other bonds. As long as they're weak and can form somewhat stable free radicals, we're good. Propagation reaction, oh, also homolytic cleavage. Just want to reiterate that. Propagation reaction, there's a few different types. So with double bonds, we've already seen this happen when we did HBr in the presence of peroxide added to an alkene. So the pi bond, this is the pi bond that's breaking, can have one electron go and interact with the X, and the other electron goes and forms a free radical. So we add the X to the carbon-carbon species. And the rest of the molecule is intact. I haven't shown it. I've just isolated the key players, the free radical halogen and the carbon-carbon pi bond. Okay, you can also have the next step in that, where it's elimination. So the reverse of that, this carbon halogen bond can break. This electron come in, that free radical come in, reform the pi bond. And so notice it's just the inverse of it. So just like addition, elimination were opposite when we were doing comparing like an E1 to hydration with acid catalyst. Same thing here. So addition, elimination are just inverses of one another. So addition to a pi bond or elimination to form a pi bond. This chapter, we will focus, or this group of free radical reactions. So we already did this in the alkenes. We're going to focus more on this, using halogen to extract a hydrogen. So hydrogen abstraction, or using an alkyl free radical like we generate here to react with a dihalogen of some sort and abstract a halogen and create a halogen free radical. Again, propagation. Let's just count real quick. We have one free radical here. We're left with a free radical there. We have a free radical here. We're left with it here. We have one here. We're left with that one. We have one here. We're left with that one. For what we're going to deal with, these two, add these together, and they end up canceling out. If you note, the X free radicals and the R free radicals cancel, and it's H2 plus XX going to HX and RX. So we're going to look at a lot of summation. And finally, any two radicals, doesn't matter which ones come together. I showed an H and a Cl in my written example. Here, I just have two X's. And again, I'm ignoring lone pairs. I probably shouldn't be so lazy, but I just want to show the key players, the single electrons. Okay, you must be able to recognize and identify whether it's initiation, forms two radicals, termination, terminates the two radicals and forms a sigma bond or pi bond, or propagation, 1-to-1. Okay. Good idea to know the names. Homolytic cleavage or coupling, those are opposite to one another. Addition and elimination, opposite to one another. And then hydrogen abstraction and halogen abstraction are two steps in an overall halogenation reaction. Okay, so free radical chlorination. This is going to be our first full-scale look at what happens with a free radical reaction. Again, you must initiate it with light or some sort of incident energy. Light is your most common form. If you do that, you can break the Cl-Cl bond, so your initiation is Cl2 going to two Cl free radicals. The propagation steps, just like we mentioned, hydrogen abstraction. This Cl free radical is going to come in this case, methane, take one of the H's from methane to form HCl, and leave behind CH3 free radical. That CH3 free radical can then engage in halogen abstraction, react with a Cl2, and form this. So I'll just draw this out real quickly. This free radical will then come here. This bond will break in this fashion. And you'll be left with H3C, Cl, check, and Cl free radical, check. Okay. The sum of the propagation steps always equals the overall reaction. And as a reaction starts to run out of reactant, eventually the radicals are going to find each other. The combinations in this soup would be two Cl's finding each other and just undoing initiation. But also two CH3s could find each other, or CH3 and Cl could find each other. This combination right here has a lot to do with what we do in the petroleum industry, where we put it into a certain high temperature. So we crack the fuel, we put a high temperature or light into it, we turn into free radicals, and they just start going crazy and forming new carbon-carbon bonds. We end up getting a crude thick oil can be converted, depending on what conditions we do it in, into a lighter, smaller, I guess, carbon-carbon chain molecule by some process like this. We start fracturing it off into smaller pieces, and those two small pieces terminate and form overall molecule is smaller than the original one. And it, I mean, depends on the conditions. You can also make it longer. You can change the nature of it, but this is actually a pretty industrially useful process. Okay, for radical chlorination, the net reactions is some of the propagation steps. So I want to just emphasize that again. So hydrogen abstraction was with the CH4 reacted with the Cl free radical to give you CH3 and HCl. The halogen abstraction, that methyl free radical reacted with Cl2, took a Cl and gave a Cl off. So if I add these two together, I should cancel out things on opposite sides. So I have halogen free radical, the chloride free radical, and methyl free radical. So I'll get rid of the two methyl free radicals, get rid of the two halogen free radicals, and you end up with the overall reaction. CH4 plus Cl2 goes to methyl chloride and HCl. Okay. Um, it if we just do a 1-to-1 ratio of one Cl2 to one CH4, then we will get mostly this. Occasionally, a second one will go on, so it's not a perfect 100% pure compound you get here. But if I want to purposely get two, then I can add a 2-to-1 ratio, two chlorines to one CH4, and then I would end up getting a CH2 Cl2. So for instance, the first methyl with Cl2 and H nu can go to 1, but if I had a second equivalent, then I can put on 2, third equivalent, put on 3, fourth equivalent, put on 4. The reality is you will always get a mix. So if I put in 1 equivalent, then I might get, let's say, 90% of this, 5%, and 5% unreacted because I didn't have enough Cl. If I put in 2 equivalents, then I might get something like 80%. That's kind of wishful thinking. Maybe 10%. Let me make that less. Maybe around 8%, 8%, 2%, and 2%. So you start getting the predominant one you want, but you get some overreaction, which means there will be less Cl2, so you're going to have some underreacted reactants as well. This, again, is a hypothetical number distribution. It would vary with temperature conditions. It would vary with light, like how you initiated it, how much light you put in. There's so many factors that come into play. But just the note that if you go to 1-to-1, you get mostly this, 2-to-1, you get mostly this, 3-to-1, mostly this, and 4-to-1, mostly that, but not perfectly 100% of anything. So methane, methyl chloride, methylene chloride, which you've dealt with in the lab or will deal with in lab a lot, chloroform, and carbon tetrachloride. Okay, so stoichiometry is going to dictate which one you get. So far, so good. So energetics, this is what we study so thoroughly that we can take this information and apply it to any other reactions and have a good sense of what's going on. So we're always going to have to focus in OChem on delta G and K equilibrium. K equilibrium dictates whether it's mostly reactants or mostly products. It's directly tied to delta G. When delta G is negative, it's favorable. K equilibrium will be greater than 1. When delta G is positive, it's unfavorable. K equilibrium will be less than 1. Delta G itself depends on the enthalpy, the energy of the bonds, if you will, and then T delta S, the entropy times the temperature at which you're doing the reaction. So if we consider this reaction, one molecule with carbon with 4 things attached, one molecule with carbon with 4 things attached, 2 atoms bonded in linear fashion, 2 atoms bonded in linear fashion, which means 2 reactants of similar shape and dimensions. So delta S, for all intents and purposes, is pretty much 0. It's not really changing. 2 to 2 of the same basic structure. So delta S is trivial, meaning this term essentially drops out, and delta G is approximately equal to delta H. So we're going to use the enthalpy, the energy of the bonds broken, to estimate the delta G and therefore the favorability of the reaction. It's not perfect because delta S may not be exactly 0, but it's good enough for what we're going to do in OChem. So if you remember, bonds broken minus bonds formed, delta H, or for me, delta H reaction is the energy of the bonds broken minus energy of bonds formed, always alphabetical, broken before formed in the equation and alphabetically. So let's go ahead and consider these bond energies. I'm sure off the top of your head you have them all memorized, but just in case, I'll put them here. 439 kilojoules per mole. I'm not big on units because as long as they're consistent units, I'm going to be fine. I'll worry about the units when I need to. 238 halogen bonds are actually a little less stable. The carbon halogen bond, notice, is a little bit less stable than the carbon hydrogen bond. Then finally, HCl, strong acid. So it associates, but relatively large number. Okay, so I looked these up, and again, these numbers are derived from looking them up on multiple sources and taking an average value. So these very likely won't match, no matter what textbook you're using, they're going to be slightly off from probably what you're using, and that's fine. I mean, that's it, it really is overrated how specific. Unless it's defined term, such as Celsius, 0 for freezing and 100 for boiling, we really don't have to stress that much about very small minor changes in numbers. So basic gist here, broken, these numbers minus formed. So these two added together minus the sum of these two. So this, you'll notice, is going to be 680-ish, like 677. This one is going to be 7 around just under 80, 776 perhaps. So 786, excuse me, apparently. So 677 minus 786, it's about negative 100 or so. That's a pretty good chunk of energy. And again, units suddenly appeared, kilojoules per mole. So in the very end, I'm going to worry about it because I may have to compare this number to others, but internally, I'm lazy with units. So I'm going to compare that to others. Had we done the same thing, the same energy for this, these numbers will all be different. So this is still the same 439. Fluorine-fluorine bonds are actually weaker than chlorine-chlorine bonds. So this is an extremely small number. So the sum of these is a little under 600. The sum of these is a little over 1,000. 600 minus 1,000 is going to be negative 400-ish. That's massive. Bromine, 439. Bromine is a little bit weaker than Cl-Cl bond. You form these, so this is going to be like 30-ish or so. This is going to be 650-ish or so, 660-ish or so. So about negative 30. Same number for this one, 439. Bond's even weaker. These two are also, though, a little bit weaker. But these numbers are relatively close with actually, for the first time, we might actually have a bigger number here than here. Not by much, but it is, so it ends up this one's positive. So what does this tell us? Well, positive number means it's unfavorable. Negative number means it's favorable. A negative massive number like this means it is unbelievably favorable. And so you will never do this reaction because the people who did it back before they knew just how energetic it was ended up literally blowing a wall off a building. Really dangerous reaction, highly explosive reaction. So when you generate that much energy, when the energy you generate is more than enough to break every single bond involved, it's out of control. So we have these numbers from a practical sense. Way too reactive. That one's going to explode. In fact, there's all the explosions right there. Conversely, the iodine, positive, useless. I have to pump energy in. Why waste time? The bromine, it is favorable, but very slow because the energy you generate is so small it can't really push this reaction along. So the reaction it happens, but it just trudges along at a little bit slower pace unless you keep pumping energy into it. If you just let it do its thing, it's going to be relatively slow. Chlorination. Chlorination is also favorable. Fast reaction, but not to the point of being explosive. It's real close, but it's not there. So from a standpoint of practicality, we don't want to blow up anything up or blow anything up. We don't want dead weights, like things that don't work and don't help us. So we pretty much just chlorinate and brominate when we talk about things in organic chemistry. Note that the chlorine reaction is substantially faster than bromination reaction. And so I want to give you a food for thought as we move on with that concept. If you've ever gone shopping for just 2, 3, 4 items, you just run to the store, get them real quick and get out. When you go too fast, and I guarantee we've all done this, you make a mistake and purchase the wrong thing. You don't quite pay attention to the label. It's a slightly different color. Let's say you get salted instead of unsalted. For a food product, maybe you get the all natural instead of the artificial. Who knows? Whatever it is, you make this mistake. So when you go too fast, you get a distribution of more things you may not want. When you go slow, you get things you want. And so you are more selective the slower you go. And that's going to be one of the things we get at is chlorination because it's so fast, you're apt to make mistakes. Take whatever you can react with, so you get a lot more mistakes or side products. Bromination, much slower, you get pretty much just one thing with a few residual side products here and there. So when we do this reaction, light or heat with peroxide to initiate it, the halogenation process will put halogen on this compound and an HX. And again, the ratio 1 to 1, we'll put one on. 1 to 2, we'll put a second one on, and so forth. Okay, so the energetics of the whole thing. Chlorination, because chlorine, you break the bond, forms an intermediate, comes and forms the next compound, so one free radical going to the product. Because this is a small amount of energy, this change here can power it along. So to be played safe, you usually add light to initiate it, but then you keep it in a ice bath to make sure it doesn't get too out of control. Bromination, much larger jump. So the amount of energy you get is less than what you need for initiation. So it can't go very fast. So the diagram hopefully shows you low activation and high delta G. It's free to pump energy back in and make it go. If you have a high activation and very low delta G, then it doesn't really generate a lot of energy to keep it propagating. So it will keep propagating, but at a much slower rate. You have to have 3 or 4 reactions kick in, generate enough energy to push it along. So they all eventually going to get their exothermics is all eventually going to go off energy of some sort, but this one takes so much longer. It's a much slower reaction. So fast, but not selective, slow, highly selective. So we'll talk about what that means in the next podcast. Hopefully this is going well. This makes sense. Next one will cover more of the math associated with it, but hope all is well, and I will see you at the next podcast. Bye.